We saw that we can put amplifier in a negative feedback loop to improve many of its desirable characteristic parameters. So how we put amplifier in a negative feedback, what will be the mode of connection of feedback network to the amplifier, that will be actually decided by the amplifier input and output impedance. So based on the input and output impedances, there are, we will see 4 classes of amplifiers. So today we will study each of those classes and we will see that how it affects, what will be the nature of the input that will be applied to the amplifier, and what will be the nature of the quantity, voltage or current, that can be more efficiently connected to the load or delivered to the load. And then it will also decide what will be the exact connection of the feedback network to the amplifier output and the input. So we have already seen this feedback loop. So this transfer function we have been designating by A, and this transfer function by beta, and this was the output, this was the external input, and here we have feedback to the amplifier along with the input, and this is the different signal or the error signal. So based upon this input impedance, we will see that this amplifier will have 4 possibilities, and then those possibilities will ultimately dictate how we connect the feedback network here at the output, and how this connection is made at the input of the amplifier. And then it will also dictate that what will be this Rin of the beta network and R out of the beta network. So all these things will be basically decided by the input or output impedance nature of the amplifier. So it will be revealed that based upon this Rin and R out, the amplifier will be categorized into 4 classes. And they will be in short called voltage control voltage source, and then second will be current controlled current source. We will see detail of each of these shortly. Voltage controlled current source, and finally the fourth one is current controlled voltage source. It is the input impedance which decides which type of source can be used with a particular amplifier. Similarly, the output impedance decides what will be the model of the amplifier on the output side. So each of these things, then they will decide the exact topology, more detailed topology of the feedback model that we just now saw. So as I pointed out, there are 4 types of amplifiers. I just mentioned their acronyms, and each of these types will be basically decided by the input and output impedances. So we are now going to designate the amplifier based this triangular symbol rather than the square one. So the first possibility is that the input impedance here, or the input resistance in the more simple case, is infinite, and the output resistance is equal to 0. So we are going to consider only 2 possible values of the resistances. they will be either 0 or infinity. So now you can see that there are four possible configurations of the amplifier. And for such amplifier, the transfer function will be designated by A naught. Then the second possibility is that the output resistance, it remains 0, but the input resistance, it also becomes equal to 0. So in this case, the transfer function will be designated by symbol R naught. So we will see that why we have different symbol for the transfer function depending upon the input and output impedances. And the third case is that we keep the Rin infinite, but this time Rout is also infinite. And for such cases, the transfer function will be designated by Gn. And the last case, of course, is that Rin is 0 and R out is infinite. And in this case, we will denote the transfer function by AI. So here we can make the other AV. It will be more appropriate to call it AV for the first case. So these are the four cases. We will study them and then we'll say that which of them are called those dependent sources, four type of sources that I pointed out. So here if you see the amplifier in this feedback model, then what we find here is that this amplifier basically senses this signal XE, and then we can say that this amplifier actually acts as a sensor on the input side, right? And on the output side, it produces quantity Y, which is of course sensed by the feedback network. So on the output side, it produces either voltage or current, V or I. So it's basically source of voltage or current, and this will be ultimately connected to load like this. So we will keep in mind that this amplifier or even this feedback network is fundamentally a sensor on the input side, and it is a source on the output side. Right. So now let us take the first type of input and output impedance scenario, and then try to see that what will be the kind of source that can be connected on the input side and what will be the output side model. So what we have here is R in to be infinite. So here we know that since Rin is infinite, so any input current is going to be 0. That means this input side, which acts as a sensor, on the input side it acts as a sensor, will not be able to sense any current. So what it will sense on the input side is it will sense voltage. Right? And we know that in general, the scenario that will be present on the input side of an amplifier is like this. There is a voltage source and there will be some internal resistance of the source and it will be connected to the input of the amplifier. So in this case, you can see that the input voltage that it will sense will be equal to Vs, and we see that presence of this Rs will actually have no impact. It will always sense the same voltage. So it will be, if we have amplifier with infinite impedance, then it will be sensing basically the voltage, and it will be more appropriate to excite it by a voltage source. Now on the output side, what we have is R out equal to 0. Right. So now question arises, what will be the model of the this amplifier on the output side? So we know that we typically use either voltage or current to model the amplifier or any other circuit output. So here we can have two possibilities, that on the output side we have this kind of scenario, that there is a output voltage present here. So my amplifier actually internally looks like this. But here you cannot connect, here you cannot assume a current source on the output side, because suppose if we try to include a current source like this on the output side, here, then we know that its input impedance is infinite, right? So to make this R out equal to 0, what you will have to do is provide a short circuit. So if you try to model in this second way, and then if I try to connect any load here, what I will find is there will be no current through the load. So this IL is always going to be 0. So I will never be able to deliver any voltage or any current to the load if we decide to use this model, ensuring R out to be 0. However, if we use a voltage source on the output side to model the amplifier, then it will immediately ensure R out to be 0. And here you can see that if you connect any load, whatever may be the load, you will always be able to feel a voltage across it. And of course, there will be some current also. So what we found is that if we have Rin to be infinite, then it will sense voltage on the input side, and R out is equal to 0 means it will be uh, behaving like a voltage source, ideal voltage source on the output side, right? And in this case, the complete uh, amplifier then can be represented in this way. So it will be excited by a voltage source, and here we will see a open circuit output voltage of VO. And the model, complete model, of course, is going to be that input side is open circuited, and on the output side we have VO, and this VO will be given by AV into V in. So AV is ratio of open circuited output voltage divided by the input voltage to the amplifier. So now if you recall op-amp, it has exactly this model, except that there are two nodes at the input side, but that is immaterial. But it also basically has infinite input impedance and 0 output impedance, and it produces a voltage which is a very large factor multiplied with the input voltage. And this is, we know that is called voltage gain. That is why we have used symbol AV here. Now here we see that on the output side, it is like a voltage source. So on the output side, it is a source, but the strength or the value of the output voltage is being decided by an input voltage, V in. So what we says that this amplifier, which amplifies the input voltage, is also like a voltage source, but it is a dependent voltage source and it depends upon input voltage. So that is why this amplifier is also called voltage controlled voltage source, or in short VCVS. So this was the first category that I pointed out in the acronym in the beginning. So what we see here is basically model of an ideal amplifier with R in infinity, R out 0. But we know that in real life, very rarely we will encounter this scenario. So what we will have in real life is real model of this type of amplifier VCVS is going to be that there will be finite impedance on the input side Rin, and of course Rin is going to be very large, and output side it will continue to be a voltage source VO, but now it will have certain output resistance, and this R out is going to be very small, and that is what happens in 741 LM741. Now we are going to take the second type of amplifier. In fact, it will be the fourth one that we pointed out, because that represents entirely different input and output resistance conditions, that we now have R in to be equal to 0, but R out is infinite. And as was pointed out, we will be designating its transfer function as AI. So here we can see that input impedance is 0. So in this case, what happens is that it will never be able to sense any voltage. So input impedance is 0. That means internally it is like grounded. So whatever you connect here, it will see this voltage V in to be always equal to 0. So this amplifier will never sense any voltage on the input side, rather it will sense current. So it will always be able to feel this I in that is flowing into it. And since it is sensing current on the input side, so typically we try to show that it is getting excited by a current source. So here it will be excited by current source, and this current source may be ideal like this, or you can have finite impedance also for this current source, and it will have absolutely no effect on the how much current flows into the amplifier, because now you can see that this current arising from the source has two paths: zero impedance path into the amplifier and this RS. So entire current will always flow into the amplifier. So this is the direct consequence of R in is equal to 0. So it is a current sensor on the input side. Now if you see the scenario on the output side where we have taken output resistance to be infinite. So here if we try to ensure that R out is 0, then actually there are two possibilities. One is that you take a voltage source, and if you want output resistance to be infinite, then you will have to make this kind of arrangement. Or alternative arrangement is that you take a current source which has infinite output resistance. Right. So in both the cases, you will be able to guarantee R out to be infinite. But if we try to connect our amplifier to a load, what we see is in the first case, in this case, this RL will not perceive any voltage. This VL will always be 0 because there is no current here. I out is 0. However, in the second scenario, if you connect any load, it will always feel a voltage minus RL into I naught. Right? So that is why we say that this cannot be the model of the output of this fourth class of amplifier, where R out is 0, and this is the correct model for the amplifier. Right? And here this output current IO. So we have already seen that it will be basically sensing input current on the input side, and it is now we have concluded that it will be like a current source on the output side, where I naught we will be calling as AI into the input current, or the transfer function, or you can say the current gain AI is the short circuited output current divided by the input current. And these two quantities, this AI and the AB that we calculated for the first class of the amplifier, both are unitless. And the model in this case now we can see is, of course, the ideal model for this class of amplifier is like this. So this is the model of the amplifier. Now if you take a more realistic scenario, then instead of having Rin exactly equal to 0, we will have it very small, right? And here R out to be infinite, we will have it very large. So the model will then get modified to that we have a small Rin and we have large R out. So even with this large R out, you can see that short circuit current is always going to be IO, given by AI into I in. But now the presence of this Rin will actually affect how much of input current flows into it. because in general you can see that it will be excited by a source. So here you can see that now Rin will get affected by the value of the input resistance. So here we see that we have current sensing on the input side, current source on the output side. So this amplifier is called uh, current controlled current source. So it is fundamentally a current source, but its value is getting controlled by an input current here. So this is CCCS. So this was the fourth class of amplifier. Now we can see the remaining one, that is the say third one, where what we had is Rin is infinite and Rout is also infinite, right? So we have seen that whenever we have Rin infinite on the input side, so if you have an amplifier with this condition, so it will always sense voltage. However, if you have Rin to be 0, it will sense current. So this is the story of the input side. Similarly, on the output side, if we have Rin to be infinite, so it will be modeled as current source. And if Rin is equal to 0, it will be modeled by a voltage source, right? So we'll keep all these things in mind. So here we can see that on the input side we have infinite impedance. So that means it is a voltage sensor. And we have output impedance to be infinite. So that means it is a current source. Right. So if we draw the model, so what we find is input side is open. On the output side, we have a current source, I naught, so that input impedance is infinite. Here it is like this. And it will be sensing input voltage, producing a output short circuited output current I naught. And in this case, so output quantity is current, input quantity is voltage. So the transfer function will be ratio of IO by V in, and this we designate as GM. And here you can see that it will have a unit of Siemens or more, right? And because it is fundamentally a conductance, we say that that too the one of the quantities on the output side, other quantities on the input side. That means they are not related to the same element. Typically, whenever we talk about conductance, we talk about voltage and current related with one particular element. Since they are on the, in this case, they are on the other side of the amplifier and related with two different elements. So we say that this transfer function is trans conductance. So fundamentally conductance, trans means related with two different elements. And more generalized model or real model for this case is going to be that we have R in, and this R in is very large, and similarly on the output side we have ideal current source with a large R out. So this R out is also very large. And here we can see that on the output side, it is basically a current source whose value I naught is controlled by input voltage. So this amplifier is voltage controlled current source. That means VC, CS. And now if you recall, transistor, whether MOS or BJT, then they are fundamentally of this nature. So the simplest real life example are MOS or BJTs. Now if you see the, this was possibly the third one, second one. So if you see the last type, which will be third amplifier that we listed. So what we will have here is Rin is 0 and R out is also 0. So R out is 0, that means on the output side what we will see is voltage. And on the input side it is going to get, or it is rather going to sense current rather than voltage. So here the ideal model is going to be a voltage source on the output side, VO, and input side is short circuited. So it will be sensing current on the input side, producing this output voltage, and this voltage will be decided by this input current. So we say that this is going to be a factor multiplied by I in. So here the transfer function or gain is going to be VO divided by I in. And here you can see that the unit is going to be resistance, and that is why this symbol was used for this case. And in this case again voltage and current, they are on the other side, so this one can be called as trans resistance. And here you can see that it is a V source on the output side, and it is being controlled by input current. So this will be called as current controlled voltage source. And if you try to do a more realistic model, then of course we will have certain Rin, and this Rin is going to be small, very small, and then on the output side we have voltage and the series resistance R out. This R out is also going to be very small. Okay, so this was the discussion or elaboration of the four extreme values in terms of impedances. Now one would like to definitely know whether such type of amplifiers exist in real life, or these are merely of academic importance. So what we will now do, we will take up MOS based circuits, which will actually be one out of these four classes. So one by one we will take example for each of the four cases. And before we try to find out the example for each of those four types of amplifier, we will quickly see the impedance behavior of single MOS at its three nodes: drain, gate, and source. So we know that these three nodes, they are going to be used in form of input or output. So we know that for ideal MOS, for ideal case, especially at the low frequency, this input impedance is always going to be infinite, right? So we say that if you look into gate, you will always see infinite. So here we are able to see that transistor indeed will be able to offer infinite impedance. Now, if you look into the drain, then in this case, it will be infinite if you neglect channel length modulation, or it will be R0, which will be very large if you include the channel length modulation. So whatever may be the case, whether no channel length or with channel length, we see that looking into drain, we have the very high impedance. Right. Now, if you look into the source of a MOS, then we know that this is going to be equal to 1 by GM if no channel length modulation is included, or it is going to be 1 by GM maybe parallel with R0 for the drain grounded when channel length modulation is included. And since 1 by GM is very small compared with R0, so it will again translate to 1 by GM. And 1 by GM is very small, definitely compared with drain case and the case of the gate. So ideal and low frequency scenario is like this. So this will give us idea that if we want to implement one out of those four classes of amplifier, then which of these three nodes should be on the input side and which of them should be on the output side. Right. So let us take one by one each of those cases. So we will start taking up those categories in such a way that the circuit is simple, and then slowly and slowly circuit will become complicated in a sense that there will be more MOS required. We will see that single MOS will not be able to fulfill all those four requirements, because here what we find is that two out of these three nodes, they have very high impedance. Only one of the node has zero or very low input impedance. So we take up example 1, and this is going to be voltage control you can guess that the simplest case is going to be of this source, voltage controlled current source. This was already pointed out. That means we have R in to be infinite and R out to be infinite. So this says it should be current on the output side, it should be voltage on the input side. And we know that a MOS in CS configuration is voltage controlled current source. So here we see that it will have R in to be infinite, and here we will have R out to be very large, and what we will get is output current. We know that it is going to be GM/VGS, and here we will have input voltage. So single MOS or single BJT is the simplest example of voltage controlled current source. Now let us take second example, and in this case let us try to take current controlled current source. So what we want is current control. That means on the input side, we should be able to, or the amplifier should be able to sense current. And for that, we know that R in should be equal to 0. And on the output side, it is current source. That means R out should be infinite. So we have seen that if you look into source of a MOS, then you can have a very low, not 0 exactly, but very low input impedance. And we know that gate is never output port or output node, so it has to be drained. So what we see here is we will have source on this side, and what we will have here is drain on this side for the of the MOS. So if you see the circuit, then we have this source, and it will be excited by certain input current, and on the output side we will of course have this output current, and R out is going to be R naught, that means very large. And here on the input side we see that R in is going to be 1 by GM, and the gate is of course going to be biased by DC. Right. So what we see here is common gate configuration. CG is the current controlled current source type of amplifier. Now if we see voltage controlled voltage source, third case, so input quantity is going to be voltage, output quantity is also going to be voltage. So since the input quantity is voltage, so that means R in has to be infinite, then only it will be able to sense voltage very well. Our output quantity is voltage, that means R out has to be equal to 0. right? So here to fulfill this, we should have here either gate or drain. So one of these two things should be here, and what we should have here is source. There is only one possibility for this node, that is source, and here either gate or drain. But we know that drain is never input quantity. In fact, it is always used for the output, so we are not going to use this one. So we have to use MOS with gate as input and source as output, right? So here we can see that we have common drain, or which is also called source follower, as the voltage control voltage source, right? But here, if you try to find out VO by V in, then this will always be less than 1. In the best case, it will be equal to 1. In the extreme case, assuming that source is offering 0 impedance. So if you want some finite voltage gain as well, because here you can see that we are giving voltage and we are interested in voltage on the output side. So if you want some voltage gain as well, then single MOS cannot fulfill, single MOS will not be able to provide us that requirement. It will definitely fulfill this impedance requirement. So we now need to modify this circuit so that we are able to have some finite voltage gain as well. So that can be done, fortunately, with slight modification. So we see that we will have to use source, because R out being 0 can be fulfilled by using source as the terminal. So source has to be the output quantity, and gate also again has to be output quantity. But now what we can do, instead of feeding the input directly to this MOS, we can first feed the input voltage to gate of another MOS, such that it gives rise to some voltage gain, intermediate voltage gain. That means first use a common source configuration to get the voltage gain, and then now feed it to source follower. Right. So here we see that if we use two MOS in this way, then we are able to meet this requirement, Rin to be infinite and RO, Rout to be low. In this case, of course, Rout is now going to be 1 by GM parallel with RL. So load itself is going to get modified. So we can substitute a current source here if we want to keep the impedance low in this way. So in this case, you can say Rout is going to be 1 by GM, because this current source will offer infinite input impedance. So this is how we can implement the third one. Now we can see the last category, which is current controlled voltage source. So as the title says, input quantity of interest is going to be current, and output quantity is going to be voltage. So to sense the current in the best possible way, the input impedance has to be 0, and to act as a voltage source, output impedance has to be also 0. So this name implied these two conditions for the impedances. Now we have seen that low input impedance is possible only when we use source terminal of the MOS. And low output impedance is also possible, or source is the only way from where you can get low impedance. So both have to be sources. Right. So here we have to then find out how to arrange. So obviously we cannot use a single MOS because then both the nodes are going to be same, and it is then pointless to connect them to same node and get anything meaningful out of it. So first what we will have to do is use a MOS such that its source node acts as the input node, and we know that gate cannot be used as the output, so of course we have to use the drain node. So this is how we convert this input into intermediate quantity. And this again, finally on the output side, we again have to take the output from the source. That means this has to be fed to the gate. If you connect it to source directly, then it is pointless. You will again get the same quantity. So in this case, now we will have this configuration. So we will have typically load here on, and we have used here current source so that the this impedance or resistance is as low as possible. That means 1 by GM. And here also you can see that Rin is equal to 1 by GM, the lowest possible that you can get out of a MOS. So we see that this fourth one cannot be implemented using single MOS. One has to use the two MOS. So these are the examples of the four classes of the amplifiers using MOS, and we see that it is possible in real life to implement these amplifiers. Now we return back to our amplifier, and we found that now we are going to use this symbol because we will see that we have to explicitly point out the series and shunt connection. So that is why we have returned back to this square box symbol for the amplifier. So here it is sensor, and on output side it is source. Input side sensor, output side source. And here we have seen that it can be either a voltage sensor or a current sensor. So we know that if we have to sense a voltage, connection has to be in a particular way, and if we want to sense current, then we have to connect our sensor in a different way. So both connections are different depending upon which quantity we are trying to sense. And similarly, this is on the source, it will be either voltage source or current source. So that also will decide how the feedback network will be connected to it. So now this feedback network has to be connected to the output side, and its output has to be then connected to the input of the amplifier. And the nature of the quantities on the output side and the nature of the amplifier input, that will dictate what will be the exact topology of connection of these two networks, amplifier and the feedback circuit. So here we know that so keep in mind that this one is source, but since it has to be fed to this network, the feedback network, so the input of the feedback network then starts acting like sensor, right? And this quantity then will be produced on the output side, and the output side of the feedback network will act like source. So it will sense either voltage or it will sense current. Similarly, it will produce voltage or current. So now we know that if we want to sense voltage, so we have to always make the connection in parallel. And if we are trying to sense current, so current sensing is done by connecting the sensor in series. So on the input side of the feedback network, we have to see that it is connected in parallel. If it is sensing voltage, it has to be connected in series with the amplifier if it is sensing the current. That means if the amplifier is producing current. Now there's one more requirement, that the output of this feedback has to be actually added with the external quantity that is being applied here. So this external quantity will get added with this feedback quantity that is being produced by the amplifier. So we have XF here, X, and that will produce XC, and each of these quantities could be either voltage or current. So then we have to see that what will be the connection topology at this location, and it will be dictated by whether these quantities are voltage or current. So for example, if we want to add the voltage, suppose this quantity is voltage, then what ultimately we want is Xc to be equal to X minus Xf, and each of these quantities are voltage. So that means there will be input voltage here, there will be feedback voltage, and error voltage will be fed to the amplifier. So we have here Vf voltage, and here we have V in, and here we have VE. So here what will be the nature of the connection? We know that although we are doing subtraction, but basically we can say that addition is being done with opposite polarity, right? So addition of voltages implies series connection. So that means on the input side, what we will have is a series connection. So here we have a voltage VE, and here we have voltage Vf from the feedback network to the amplifier, and then here we have input voltage. So we know that if we connect these voltages in series, what we will get is sum of these two voltages, right? So here you can see that VE and VF, they have been added in series. So now we can connect them in this way. So here you can see that V in is going to be VE plus VF. That implies VE is V in minus VF. So we have to see that which quantity we have to deal with on the input side to decide what will be the exact nature of the connection. Okay. Similarly, suppose we have to supply current. That means we have I in here. We want to do IE to the amplifier, and we are feeding back current. So we have to basically add currents or subtract, it's the same thing. And we know that they always have to be do in parallel. That means these two connections here, now they have to be in parallel. So we have current I, so that should go here and to the amplifier. So similarly, so we have I in here, so there will be XIE and there will be IF. So here you can see that I in is equal to IE plus IF. This implies IE is I in minus IF. Now similarly on the amplifier output side also, we can have a parallel or series connection. So here we have our amplifier and it is, suppose it is producing output voltage. So my feedback network, it should be V sensor. So it is a voltage sensor, so it has to be connected in parallel with the amplifier like this. And once the feedback network is voltage sensor, it uh, becomes apparent that its input impedance R in beta has to be infinite. Similarly, if we have amplifier and it is producing output current, so feedback network should sense current, so it has to be connected in series. Right, so its connection should be, let me modify, same current should flow through this case. So same current should flow through the beta network also, and it immediately points out that R in beta should be equal to 0. So we see that the impedance of this amplifier network dictates everything. It says what are the quantities that can be there on the input side. Similarly, what are the quantities that you can get on the output side. What should be the impedance requirement of this beta network. What should be the topology on the input side. Similarly, on the output side as well. So these two quantities, R in and R out of amplifier, they are very important. References are Rajavi or Sidra Smith.